All right, hello everybody. Today we're getting going with chapter 12, which is all about circles. Okay, now obviously we've talked about circles a whole bunch through this course. Okay, with chapter 12, what we're going to do is look at some more properties of them, go more in depth, and take a look at more things we can figure out about them. Okay, 12.1 is all about tangents. Okay, tangents to circles. We'll tell you what the heck that means. We'll give you one property, and then that property is going to lead to a whole bunch of different things we can figure out using both the property along with a lot of different stuff we've done so far in this course. Okay, so a lot of stuff gets reviewed as we go through this section. All right, so first off, what is a tangent to a circle? Okay, I'm going to say it's a line that intersects the circle in exactly one point. Okay, so I've got a circle, I've got a line going through it, and there's a single spot these two come together. There's exactly one point, and we'll call that the point of tangency. All right, then we're going to give you one property about tangents to a circle. Okay, in our theorem 12.1, I'm going to say that if a line is tangent to a circle, then the line is perpendicular to the radius at the point of tangency. Okay, in other words, if I have a tangent to a circle, and we'll say the point of tangency is point P, and I make the radius from the center of the circle 2P, okay, so if this is a tangent line, I'm going to say we have a right angle right here. Okay, it might not seem like a big deal right now, but like I said, what we're going to do is show you a whole bunch of things we can figure out about circles, okay, based on that one property. Okay, the first one we'll look at finding some angle measures. Okay, problem 1, part A says ML and MN are tangent to circle O. What's the value of x? Okay, so what I have here is I have a circle with two tangent lines, LM and MN. And anytime you hear tangent to a circle, the first thing you should probably do with that problem is draw right angles in. Okay, when you think tangent, think right angle. Okay, what's the value of x? In other words, what's the measure of this angle? Well, basically what I have here is a quadrilateral, a 1, 2, 3, 4-sided shape. I know 3 of the angles. I know all 4-sided shapes should add to 360. So what I can do then is I can just say x is equal to 360 minus the 117 we're given in the problem. Okay, then minus the two 90s here. And that'll give us our last angle, so 360 minus 117 minus 90 minus 90. When I plug that in my calculator, I get a 63 degrees. Okay, so one thing we can use that tangent property for is finding angles. Part B is the same idea. It won't use 360 though, it's a different shape. Why don't you pause the video, give part B a shot, and then hit play to check your answer out. All right, part B, ED is tangent to circle O. Okay, so when I hear tangent, I want to think 90. What is the value of x? Okay, well, x is one of the angles in a triangle. I know triangles always add up to 180 degrees. So this time what I'll do is I'll take 180 minus the 38 we're given, okay, minus the 90 we got from the tangent. Okay, so 180 minus 38 minus 90, we end up with 52 degrees. All right, for a missing angle in that triangle. All right, moving on to problem 2. What else can we do with this tangent theorem? Okay, well, we can find radiuses of circles. Okay, so here in part A, what's the radius of circle C? Now, with this one, notice we want to figure out what the radius x is here, and we didn't actually make any measurements within the circle. Okay, we just have a tangent to the circle, and we have another measurement meeting up to the circle. Okay, why would this be important? Well, this right here is actually why we know how big the Earth is. Okay, we know how deep it is. We've never drilled to the center, okay, because it's too deep. But if we make measurements like this on the outside of it, we can use some geometry to figure out what the actual radiuses are. Okay, so let's go ahead and do that here. We've got a right triangle. We're solving for lengths. So hopefully the thing coming to mind is a squared plus b squared equals c squared, Pythagorean theorem. Okay, because I have a right triangle here. Well, let's plug in what we know. The a we can say is just my x. Okay, plus b squared. Well, what is my b going to be? That's the other side length here, which is the 12. Okay, the other not hypotenuse. So 12 squared is equal to, then here's where it gets a little bit ugly. Notice my hypotenuse is made up of two parts, an x and an 8. So I'm going to say my hypotenuse is this, x plus 8 squared. Okay, so to solve this, we're going to have a little bit of algebra practice. So I've got x squared plus 12 squared, I know that's 144, is equal to, and then how am I going to deal with this? Well, when I say I'm squaring something, that just means I'm multiplying it by itself. So in other words, x plus 8 times x plus 8. And then reminder, how do I multiply two binomials, two-term factors together? Well, one way to do it, or one way to think about it, is with the FOIL method, where I multiply the first, the outer, the inner, and the last, and just add all those together. Okay, so let's do that here. First, x times x gives me an x squared. All right, outer, x times 8 is going to give me a plus 8x. Okay, inner, 8 times x, we can say is another plus 8x. And then last, 8 times 8 will give me a 64. Okay, so when I expand the right side out, when I FOIL things out, this is the mess I end up with. Left side, I've got x squared plus 144. Okay, now this is starting to look kind of ugly. It's actually not that bad though. Let's take a look at what happens here. Notice there's an x squared on both sides of the equation. So if I subtract x squared on both sides, they'll just cancel away. So this actually isn't a quadratic equation, it's just with x's. So what I'm left with then on the left side is a 144 is equal to 8x plus 8x is 16x. And then plus the 64. Now we're down to a pretty simple equation we've been solving all year. Okay, we can do this. Subtract 64 from both sides. That gives me an 80. Then to finish things off, as I run out of room here, divide both sides by 16. And I end up with x equals 5. All right, so in other words, the radius of this circle would be 5 units. Okay, again, a little bit of algebra in this one. It does look a little ugly at this part, but the nice thing about a problem like this is it's always going to clean up pretty nice for you. Things will cancel down to an equation you're able to solve. All right, that's part A. Part B is the same idea. I want you to pause the video, run through that one, and then hit play to check your answer. All right, let's run through B here quick. A squared plus B squared equals C squared because tangents give us that right angle, so we have a right triangle. I can say A is my x. I can say B is the 10. And if I flip the order of those, really doesn't matter, is equal to C squared, which is going to be this entire chunk, which is made up of an x plus a 6. Okay, so we have x squared plus 10 squared, which is 100, is equal to x plus 6 squared, means the same thing as x plus 6 times x plus 6. Okay, let's FOIL that guy out. First, x times x is going to give me an x squared. All right, outer, x times 6 is going to give me a plus 6x. Oops, color-coded wrong there. Inner, color-coded wrong. Oh, nope, that's right. 6 times x is plus another 6x. And then last, 6 times 6 will give me 36. Okay, as you do a couple of these, you're probably going to see some shortcuts you can take. You can combine things in steps, but we'll expand it all out here. So x squared plus 100 is equal to x squared plus 6x plus 36. Now, right off the bat here, I can just cancel out these x squareds. If I subtract x squared from both sides, they go away. So I have 100 is equal to 6x plus 6x is 12x plus 36. And then from here, just subtract 36 from both sides. That gives us 64 equals 12x. And then just divide both sides by 12. We end up with x is equal to 5.3 repeating, we could say. All right, part 3, let's take a look at a applied problem of that example. So it says the CN Tower in Toronto, Canada, I think that stands for Canadian National Tower, okay, has an observation deck 4.45 kilometers above ground level. Okay, about how far from the observation deck is it to the horizon? And it's going to tell us the Earth's radius, which we'd find doing the same thing we did in the last problem. So what we have here is we have a tower that's sticking out way above the surface of the Earth. Okay, this isn't to scale, obviously, but it's above it. And we want to know how far is it to the horizon. In other words, how far can we see across the Earth, given we're looking from that tower. Okay, once again, what we have here is a squared plus b squared equals c squared. And the reason for that is your line of sight to the horizon is going to be the same thing as a tangent line. Okay, if you're looking at that specific point where the Earth curves and you can't see any further, that's a line that's tangent. So I know that once again I have a right angle here, so we're talking right triangles. Okay, let's plug in our a and our b. We could say a is this distance we're looking for here, this x. So we have x squared plus the b we could say is this 64,000 squared. Okay, is equal to then my hypotenuse, kind of like in the last problem, we made up of 64,000 plus the 0.5. So we could just say 64,000.45 squared. Okay, so we got to solve this guy for x. Now, something I don't want to do with this one is I don't want to plug these numbers into my calculator and deal with really huge numbers to be writing out and subtracting. So here's what I'm going to do. I'm going to do this all in one step on the calculator. I'm going to subtract 64,000 squared from both sides. And I'm not actually going to combine anything. I'm just going to say that leaves me with x squared is equal to 64,000.45 squared minus 64,000 squared. And again, I'm not going to plug those in. I don't care what these big numbers are equal to. I care what the answer is. And then for a last step, what I'll do is I'll take a square root on both sides of the equation. So in other words, my answer then is x is equal to the square root of 64,000.45 squared minus 64,000 squared. And what I'm going to do then is plug that in one step, which is going to make just the numbers, the large numbers that I have, easier to deal with. Let's pull my calculator up. Let's get my face out of the way. All right, so what that's going to look like in one step, pretty straightforward. Second square root symbol, and then just plug in what we see. All right, I end up with 75.9, we could say. Again, the advantage of doing things this way is I didn't have to deal with a bunch of large numbers. I let the calculator deal with those. So we could say answer then is 75.9 kilometers. All right, nice little application of tangent problems. Okay, two more quick theorems building off the main one we looked at, that tangents are perpendicular, okay, to the circles. Okay, first one is just the converse of that. Okay, if a line in a plane of a circle is perpendicular to the radius at its endpoint on the circle, then the line is tangent to the circle. Okay, so in other words, if this line is perpendicular to the radius at this point, okay, that means that our line is a tangent line. That means we're only intersecting the circle at one point. Well, what can we do with that? We can ask the question, is a line tangent to a circle? Okay, so in this case, is ML tangent to circle N at point L here? Okay, so in other words, what we want to know, is this a right angle? Or in other words, are we looking at a right triangle? Okay, we already know how to determine if triangles are right or not. What we'll do is we'll look at a squared plus b squared. Okay, so in this case, if this is a right triangle, that'd be 7 and 24, the two smaller sides. When I plug that in, I get a 625. And what we'll do is we'll compare that to c squared, okay, which would be my 25 squared. And I know that's 625 as well. Okay, so we just showed that a squared plus b squared equals c squared in this case. Therefore, we have a right triangle, which means that angle L here is a right angle, okay, which means that LM is tangent. So we just say yes, ML is tangent. Okay, so essentially just doing a right triangle check we did a few chapters ago. Problem B is the same idea. I want you to pause the video, work through that, and then hit play to check your answer. All right, going through part B, are we showing a tangent line? Well, we want to see, is this angle a right angle? To do that, we'll look at a squared plus b squared. In this case, that'd be 6 squared plus 2.5 squared, which I end up with as 42.25. We'll compare that to c squared, which is 7 squared, which I know is 49. Okay, those aren't equal. We just show that a squared plus b squared is not equal to c squared. Okay, therefore this is not tangent or not a tangent line, however you want to say that. All right, last theorem we're going to look at quick. It says that if two tangent segments to a circle share a common endpoint outside the circle, then the two segments are congruent. Okay, so if we have a setup like this where both AB and CB are tangent to the circle, and since they both share point B outside the circle, so we have two tangent lines that meet up at the same point outside the circle, okay, our theorem says then the two segments are congruent. In other words, AB and CB have the same length. One more definition we'll add to that, the idea of an inscribed circle. I'm going to say a circle, it's a circle with all sides of a polygon tangent to it. In other words, it fits within that polygon, hence the in part. Okay, so if I say that circle T is inscribed by triangle XYZ, that means all these lines XY, YZ, ZX are tangent to the circle. They intersect at one point. Okay, the circle fits perfectly within that shape. All right, so let's go ahead and use that theorem here quick. It says circle O is inscribed in triangle ABC. What is the perimeter of triangle ABC? Now with this one, I'm given a few different measurements. And since I know these are all tangents because they're inscribed, I know that, for example, AD and AF will be congruent to each other. They'll have the same length of 10. Same thing with DB and EB. They'll be congruent. Both have lengths of 15. And then FC and CE will both be congruent because, again, they're tangent to the circle and they also intersect at a point. So my perimeter then is pretty simple. We'll just say P is equal to 10 plus 10 plus 15 plus 15 plus 8 plus 8. So what do we have here? 30, 40, 50, 58, 66. So we can say our perimeter is 66 centimeters. Okay, last question, problem 5, part B is the same idea. I want you to pause the video, work through that problem, then hit play to check your answers out. All right, problem B, again, we have a circle inscribed in a polygon. Therefore, all the lines are tangent, so that both these segments will have lengths of 8. Both these segments will have lengths of 16. These will both be 9s. And these will both be 6s. Okay, Okay, so the perimeter will just be adding all those chunks together. 8 plus 8 plus 16 plus 16 plus 9 plus 9 plus 6 plus 6. And when I add that all up, we end up with a 78, so we could say 78 centimeters for a perimeter. All right, there you go. There's section 12.1. Big thing here is when you hear tangent to a circle, think right angle. And really, there's a lot of simple questions that we've already solved this semester, just kind of adding the tangent part to it. Give the homework a shot. Let us know if you need help, and we'll see you guys later.